Hey Chemistry, Mrs. KJ here, going over 2.02, the nuclear atom. An atom is composed of subatomic particles, protons, neutrons, and electrons. In this lesson you will continue learning about the structure of an atom and how scientists explored that structure. After gaining an understanding of the experiments of Ernest Rutherford, you will learn about three subatomic particles that make up an atom. Goals for this lesson: describe how the experiments of Ernest Rutherford helped determine the nature of the nucleus. Describe the structure of an atom and its subatomic particles. Identify protons, neutrons, and electrons and their mass relative to each other. So, we have atoms. We have the atomic model was further developed by Rutherford using his gold foil experiment. Atoms made of particles. Outside the nucleus can be found electrons, and the particles inside the nucleus or part of the nucleus are the protons and the neutrons. All right, so slide 2 is where you can get your study guide from. And I'll go ahead show you. I put our first paragraph, our goals, our keywords and pronunciations. Neutron, an electrically neutral particle with approximately the same mass as a proton, found in the nuclei, so the center, the nucleus of atoms, along with protons. Protons, a positively charged particle found in the nuclei of atoms. So nuclei is plural for nucleus. We don't say nucleuses, we say nuclei. Experiments led to increasing understanding of the atom. Science can be like biting into a piece of candy and just as much fun. We are often surprised by what we find once we bite past the outer covering. Penetrate the outer coating of a chocolate-covered cherry, for example, and you are in an entirely different universe of taste and sensation. Experimental work in science is like that. As scientists experiment, they go deeper into areas that they were not familiar with before. Ernest Rutherford and his team made it to the cherry center of the atom, much to their delight and surprise. There they found something totally unexpected. In this lesson, you will learn how they did the experiment, what they found, and what it means for your study of chemistry. So, experiments sometimes give unexpected results, just as a good piece of chocolate might give you a nice surprise. Ernest Rutherford set out to test Thomson's plum pudding model of the atom. J. Thomson used a cathode ray tube to discover the electron, and from that result he devised his model of the atom. Thomson's model suggested that negatively charged electrons are suspended in an atom made up of positively charged particles. His model resembled a serving of plum pudding in which raisins are scattered throughout the pudding. But did the plum pudding model suffice to explain the structure of the atom? Scientists seriously debated the question in the years around 1900. Physicist Ernest Rutherford set out to test Thomson's plum pudding hypothesis about the atom. All right, so we got our timeline here. We had Dalton back here in 1800, Napoleon, American Civil War, 1900s. We got our cathode ray. For J. Thomson's cathode ray experiment provides the existence of electrons. In the 1900s, Ernest Rutherford's gold foil experiment discovers the nucleus. And 1909, Robert Millikan's oil can drop experiment determines the mass of the electron. Ernest Rutherford discovers a positively charged nucleus at the center of the atom. So he went with this model of the atom, which is different than what Thomson said. So this was the plum pudding. J. Thomson discovers that atoms have negatively charged particles called electrons, and he thought they were just kind of scattered all over in the positively charged mush. And Rutherford's like, no, it's more this design. And Chadwick discovers the neutrally charged particles in the nucleus called the neutron. And he said it's very organized, and then you have more unorganized electrons around the outside. You are not going to be tested on the dates for any of these. Sorry if you were worried about that before I didn't bring it up. But no, you're not tested on the dates. It's just kind of nice to see how it progresses. Rutherford found that some experiments yield unexpected results. In his experiments, Rutherford bombarded a piece of gold foil with a beam of radiation containing alpha particles. He shot the alpha particles at a piece of gold foil that was circled by a fluorescent screen. What Rutherford saw surprised him. Most of the alpha particles did in fact seem to pass through the gold foil completely unhindered, so they just went straight through, no big deal. That was consistent with Thomson's model, but strikingly, some of the particles were deflected way off course. A few were even sent bouncing back at the source of the beam, as if they hit a solid object. Rutherford correctly concluded that the positive charge of the atom was densely concentrated somewhere inside the atom, and not spread out as Thomson suggested. All right, so why alpha particles? And what are alpha particles? Alpha particles are positively charged particles that are emitted by radioactives such as uranium. So it's a whole stream of positives. And if Thomson's plum pudding model was correct and the positive parts of the atom were all spread out, the alpha particles should have passed easily through the gold foil because the diffuse positive charge would not pose much of an obstacle to the alpha particles. Instead, he had some things bouncing back and all over because when the positives hit the really dense positive nucleus, two positives, are they going to repel each other or attract? They're going to repel each other. All right, so we got Rutherford here and his gold foil experiment. Rutherford created the plum pudding model of the atom by aiming a beam of alpha particles at a sheet of gold foil. A sample of radioactive material in a glass tube sitting inside a lead box would emit alpha particles through the opening in the front of the box. Rutherford hypothesized that the alpha particles should pass straight through the gold foil and leave a mark over here on the zinc strip, directly behind the foil. So it should go really nice in a straight line. All right, so he had this radioactive material, and the radioactive material is automatically shooting off these alpha particles. He had it inside this lead box so that the alpha particles could only escape through that little hole. So that's how he controlled it. Hit a piece of gold, should have made a mark right there. Model was correct. The alpha particles should pass directly through the atom and should only be deflected slightly when they get near the electrons. So you would have had these types of results. So he shot it through, and you can see that this is what really happened. Most of them are going through, but because you can see that there's all kinds of marks over here, and yet, look, you have a few randomly here, a few back, and so when we release those alpha particles, that's what's shooting out. We're releasing those alpha particles. Again, you see most of them go here, but you did have some deflection. And that deflection is what made Rutherford say, hey, this isn't right. His model can't be right, or we wouldn't have all these deflections. Rutherford found that most alpha particles hit the zinc strip behind the gold foil as expected, but a small number were deflected back at a much sharper angle back toward the lead box. So then he could say, okay, most are going to end up here, a few here, a couple over here. So he looked at his probability. Strong positive charge must be condensed in the solid nucleus of the center of the atom in order for the alpha particles to be deflected at such a sharp angle. Because if there's just a little bit of positive, it would just kind of like, oh, whatever, here, move over. But this one was so strong, it came in, it was, put those brakes on, bounce way back. Rutherford had discovered the nucleus of the atom. Rutherford now had evidence that contradicted the plum pudding model. It appeared that each atom had a massive center, or nucleus, massive compared to the mass of the electron. So massing meaning that's where most of the stuff is, most of the weight. I know mass and weight are different, but it helps sometimes to think of it a little bit more of like the weight. So that's where all of the mass is, versus if you look at the atom as a whole is this big, you can see there's a lot of empty space, right? You can see it's really compact here, and then lots of empty space except for the electrons. Side note, these paths that the electrons are going on are not really there. They just draw them in to show you where the electrons might be going. It's kind of like the Earth going around the sun. There's not an actual racetrack that the Earth is following, although you know in the pictures they always draw the orbit. It's the same idea. So really it's this whole space, lots of empty space, some little electrons, and a very dense, solid nucleus. The model resulting from Rutherford's work suggested a positively charged nucleus and negatively charged electrons outside the nucleus. Most of the atoms seem to consist of empty space, which I know is weird to think that most of the atoms that make you up are empty space. Because then you think, well, then why can't I see through myself? It's because they're so tiny overall. It's really hard to try and conceptualize that. After discovering that the nucleus had a positive charge, Rutherford hypothesized that this positive charge was the result of individual positively charged particles. He called these particles protons. He went on to conduct a series of experiments that confirmed that positively charged particles did exist in the nucleus of an atom. So he said it's not just one big positive solid ball, but there's actually a bunch of little ones, a bunch of protons inside. Proton, a positively charged particle found in the nuclei of atoms. So Rutherford is important, and his gold foil experiments showed the nucleus, or the center of the atom, has a positive charge, can have many protons, so in other words it's made up of little pieces that are positive, not just one big clump, and it's very dense. The atom is mostly empty space with electrons orbiting the nucleus. James Chadwick presented evidence that the nucleus was made up of protons and neutrons. Rutherford also guessed that there were some neutral particles within the atom's nucleus. Later, an English scientist named James Chadwick, who spent much of World War I in a German prisoner of war camp, confirmed that neutral or uncharged particles did reside in the nucleus with the protons. Chadwick, in 1932, called these particles neutrons. Independently, both Rutherford and Chadwick won Nobel Prizes. They stood on the shoulders of Thomson and Millikan. In other words, they needed the previous work to do theirs. From the work of scientists such as these, we know the fundamentals of the atom that Democritus wondered about 2,000 years earlier. James Chadwick's studies show that the nucleus contains uncharged particles known as neutrons. And he said it was very organized, and then he said the unorganized electrons around the outside. So Rutherford's name is definitely more well-known than Chadwick, although personally, I find it more impressive that Chadwick could discover neutrons since they're neutral. I mean, Rutherford had the advantage of positive and negative, attracting, reflecting. He managed to discover neutrons, which are neutral. So I was always most impressed by that one. Scientific study leads to an understanding that an atom is composed of 3 subatomic particles. Piece by piece, people unravel the mystery of the atom. The nuclear atom concept envisions the atoms as composed of 3 small or subatomic particles. And I'm going to stop there. Let's add that to our vocabulary list. Subatomic particles, what atoms are made of. Specifically, the protons, electrons, and neutrons. The nucleus is composed of positively charged protons and neutral neutrons. The nucleus is encircled by negatively charged electrons. Take some time to examine some of the properties of each subatomic particle. So again, electrons are negative. You need to know that. Protons are positive. Protons are positive. You got to know it. Neutrons are neutral. Protons and electrons have exactly opposite electrical charges. So, in other words, protons are +1, electrons are -1. An atom that is electrically neutral, that is, that has no net electrical charge, will have the same number of protons as electrons. Almost all of an atom's mass is in the nucleus. The mass of an individual proton is the same in all atoms, no matter how many protons the atom has. So all protons weigh the same amount. The mass of a proton is huge compared to the mass of an electron. So the proton would be like the weight of your body, an electron would be like the weight of one hair on your head. Neutrons are similar in mass to protons, but they have no electrical charge at all. They are electrically neutral. And we'll add to our notes in the next video that we make.